Nishka Rao is a bachelor student, bachelor degree bachelor student. He got PhD position in the United States, and he's working with me. He's now from Indian Institute of Science and Science Education and Research from India. Welcome.
Yeah. Hello. Thank you for the organizers for organizing this and giving me this opportunity. So I'm Nishkul. I'm from IISA Pune, and I'll be presenting on the enigmatic nature of black holes. It'll be a pedagogical come gravitational wave observational talk. Um, to begin with, so I think everything is fine, right? We can see the screen. I'll be using the board in between for some of this, and some of it will be just the screen. Yeah, so the idea is quasi-local definitions of black holes. So, black holes, they are the Einstein solutions to the Einstein's equation in relativity, and they are like extremely non-linear, extremely puzzling. And until very recently, we didn't observe them directly. We are observing them now directly through these Event Horizon Telescope observations. The idea is defining the horizon. That's actually a very tricky problem because although intuitively it's very simple. Horizon is something where out of, like if you go inside, light cannot escape out of it. But to define it, how it's done usually, conventionally, was through the global picture. So if I think this is visible, right? Yeah. So yeah, I more or less it's in the slides too, but the idea is in a physical black hole, there's the scribe plus, which is the null infinity, where all light rays go like at late times. So the idea was we collect all the light rays here and trace it backwards. So black hole was defined as the solution. So you have an asymptotic flat manifold. First of all, asymptotic flat. That's a notion which is basically saying that it's Minkowski at very far distances. Not all physically realizable spacetimes are asymptotically flat, but there have been like adjustments to the notion of black hole. So you have this manifold, but you subtract the causal past of scribe plus. So what you do is you trace back all the light rays, and that gives us a notion of uh, which parts of the space-time where the light rays don't come from. So this is known as a black hole, and the boundary of it is defined by the closure of, I think, closure probably in like it could be written a dot or partial. That's the way it's notion. This is known as the horizon. So the idea of a horizon is a smooth null hypersurface which separates this. But the problem is this is global, as I think last week also some of you pointed out in the seminar. This notion is hard if you want to study things locally. One thing is numerical relativity. We like say a binary black hole simulation is run. At the end, you don't want to wait till the end to actually trace back where the black holes are. So this is somewhat of a teleological problem which is solved by the notion of trapped surfaces. So I'll actually introduce trapped surfaces in a slightly different way. This is not how it's done historically, but uh, two things which I'll use further. So I'll be defining this Newman-Penrose tetrad. So first of all, in the way special relativity is done, it's done as space plus time. Space-time is space plus time. But that's not actually physical because our space-time manifold is not like there's a gauge choice which you have to do to get it into 3 plus 1. The physical notion of the spacetime, as we know, we want to study light rays, is by null geodesics. So we'll be studying something called null geodesic congruences. So null, why we want light rays? Geodesics are non-intersecting. Like okay, sorry, congruences are non-intersecting. Geodesic is nothing but you parallel transport along the manifold. So it's so you have the null geodesics. They have a tangent vector, like the affine parameter has a tangent vector, so del by del lambda if your parameter is by lambda. So you parallel transport it along the manifold, and that's a geodesic. So there's a acceleration equation which is conserved. So we will be using null geodesics, and we'll be using two sets. So simple thing in a Minkowski spacetime, you always can do local coordinates such that you have t and r, right? You will suppress the other dimensions. So you'll have t plus r and t minus r. So these are the two principal null directions, and we'll be considering two null vectors along those directions. One we can call outgoing and ingoing just based on that notion. So this defines a local null tetrad, but as you can see in the plot, it's on the light cone. That's just two. There are other two dimensions. The transverse one, where we'll have two other tetrad vectors. So I'll be calling L, N, M, and M bar. So out of this, three are independent. One is determined from the others. This gives a local formulation, which I'll be alluding to later. So all my definitions I'll be basing on this notion. So, yeah, as I repeated, these are the null tetrads. You can write the metric as in the slides in terms of this local null tetrad. So for this, I have the, do I have laser? Okay, probably I'll just, this orthonormal, which we define like there's a notion of normalization which you define, which is L dot N is -1 and M dot M bar is 1. And then that gives the, like they are null. So all these three are independent and one is you can determine from the others. So that gives me the local metric. And also an interesting quantity is the induced metric. So there's this cross section N, right? So we have this horizon, I mean, it can be anything for now. We'll have the cross section, which is the two dimensions. We assume two-dimensional spheres foliated. So we have a cross section N and a horizon. I mean, for now, let it be anything. So we have this metric here, which is important, which is to give the full notion. So I'll be coming back to this multiple times. So this is more or less the setup. These are some, so in Newman-Penrose, the power is to actually encode all these quantities into some antisymmetric terms. So antisymmetric because off diagonals cancel. So we'll actually work with much lesser terms. So if you actually do the normal way, you'll have, I think, 20 degrees of freedom of the Riemann scalar, which you actually can encode in 12. But since you use complex conjugates, you use just 6. So it's a very powerful formalism. And a lot of them have physical intuition. This is just like these are the, like what it actually physically represents is, say, you have these vectors, right? Let's take two of them. Now I consider something along this, let's say A and B. Now when I move B, how does A change? So that, how does the entire tetrad change when I move B? So that is one term, delta A, B, A. So these are the scalars that I represent. So I think epsilon is related to the geodesic acceleration, some of them related to expansion shear, which I'll come later. So these are physically motivated quantities, but also it's a very neat way to encode. There's not just this, I've not put all the equations, it's because it's very scary looking, but it's just, I'll probably write it. These act like the connection. Gamma is encoded into some scalars, which can be like epsilon, rho, sigma, etc. I'll be coming back to that. The Ricci scalar Riemann tensors are encoded into Weil scalars, psi 0, psi 1, which I think you would have heard in the gravitational waves also, because psi 4 is something which will be coming back and forth. So this is how the Newman-Penrose setup is. And now to actually, focus on light and actually focus on focusing light. So how does light focus? So the idea is gravity focuses light, but we want to formalize it. So the notion is you have light rays. Yeah, probably is the how much is this?
You can go that much.
Okay. So you have light rays. They are, I don't know, I take it as L. Okay. L is the like the null tangent vector. What we are interested is in this deformation vector, which is delta alpha L beta. This actually basically says the rate of change of L across the geodesic. So that gives us how it actually moves. We want to know the evolution. The idea is this is a second order rank to tensor, and it can be decomposed into symmetric trace-free tensor. Okay, first of all, it's trace. So there is a trace of theta that gives us some quantity which I'll call theta. Okay, this is also theta, so I'll just give a hat for it. This is the deformation tensor, this is the expansion, and there's a shear, which is the symmetric part minus the trace and h. I'll always have the metric, which is now see I'm using the induced cross section metric, not the entire metric. So whenever here to when I take the trace, it's with the h. So it's h alpha beta, theta alpha beta. I think I did put that. Yeah. And there's the antisymmetric part, which is usually zero because we assume hypersurface orthogonal, and that there's a Frobenius theorem in pure like differential geometry, which actually says that that is zero, the torsion. And here you can see how there are these Newman-Penrose scalars that come in. So the expansion is related to rho, the expansion of the other null normal is related to mu. So there are some symmetric transformations from L and N. You can actually get through all of this. Interesting properties, this is zero, the torsion is zero, so we'll be getting other like constraints on the Newman-Penrose scalars. So, yeah, the physical picture, expansion, like the easiest way to think about all this is fluids. Expansion is literally an expanding fluid. The area is like expansion can be locally defined as the area of, at a later time by the area at a present time. Shear is the like the rotational component of the fluid, and twist is literally the twisting. So these are named very well. So the interesting thing is there's this Rai-Chaudhuri equation. So I had the expansion. If I take the coherent derivative of the expansion, that's actually simplified as this. It's not, it's an easy calculation which can get to this. But now there's some interesting aspects. So this was derived. But after this, what comes forth, I think Penrose did it in later years, which was very interesting because, as I told, omega can be zero. Omega is basically this, which we, by Frobenius theorem, we say that omega is zero. Sigma, you can assume a shear free congruence to start with because you can do a null transformation which will give you a shear free. So what you're left with is this, and R. Now in GR, you can assume, like the classical GR, you can assume null energy condition, which will make this like R acting on LL is less than or equal to zero. So that'll give me this fundamental equation. So this is actually interesting. I'll probably write it down. So d theta by d lambda plus half theta square is less than zero. Yeah. So the idea is so first of all, this is always positive. So this being less than zero implies that this is always negative. So now there are two cases. You start with theta greater than zero, theta less than zero. If you start with theta greater than zero, okay, we'll actually assume equal to zero for now. This is true when it's vacuum spacetime. This term is zero, so exact equality holds. So for vacuum spacetimes, you can derive, I think theta will be 2 by lambda plus some constant, 2c or something. So, which is like theta at lambda naught. So, I think, yeah, this is like, this is fixed by theta at lambda naught. So, you can start with theta at lambda naught greater than 0 or less than 0. If you start with greater than 0, it'll always go to 0 at later times. So, it's a easy, like at vacuum, you can prove that. But the interesting case is if you start from less than 0, this is when it'll always go to minus infinity. So, in a finite time. So, this is the problem. And this observation actually Penrose made, and it came into the singularity theorem. Like one of the important point in the proof is if you start with a negative expansion, it'll eventually converge. So you'll have null geodesics going, and like at a point which like this is not a physical point in the space time. So this problem was actually observed through this fundamental equation. So I'll not go into the singularity theorem.
So the sigma, you don't need to consider initial surface it is zero to write down this inequality, because you can see the sigma is negative sign in front of that.
Yeah, for the equality you need, but for you can always write this because this is a positive form. But however, this is always zero. But this, yeah, I agree, correct. Thanks for pointing it out. Okay, so now this is how we define the notion of the physical notion of Newman-Penrose. We can actually start getting into quasi-local formalism. I think one of the important points which last week also was addressed was trapped surface. So trapped surface deals with the expansion. As you can see, future trapped surfaces are defined when at a point both theta L and theta N are less than 0. So it implies that at a point, both outgoing and ingoing light rays converge. So this type of, like you can actually think of an experiment in this room. I shine a spherical laser. If it starts, if like after a later time, if it's smaller than where it was at the end, then we are inside a black hole. But actually we are not. So it always expands, right? This is important because if you notice here, this theta L, theta N is calculated just at one point. So I should be clear here. One point as in somewhere here in the space line.
So I have a question. So
Yeah.
when theta is positive, that means you are outside trap surface, and when
Yeah.
you are it is negative, you have instead started from inside, right?
Yes, I mean, yeah, like this definition of trapped surface, when it's negative, you are inside the trapped surface. There's also marginally trapped where you assume zero, but yeah, that's the distinction. So you can actually, this diagram, is it clear? So here, if you see, both expansions are positive, but here both are tipping in. Oh, this is the trapped surface. So I don't think it's drawn inside this, but if
The
you,
trapped surface is that
this one,
yeah,
right? Yeah, but yeah, it's not drawn inside that. So if you see there, both expansions are negative.
No, that is drawn there. You can see the inner boundary of this cone.
This-
from the trapped surface. From the trapped surface, yeah.
Yeah.
So you can see a cone there, the smallest cone from the trapped surface.
Oh, this one.
Yeah.
This
So
B equals constant.
so yeah. So that B3, what
Oh,
it is
okay,
showing,
okay.
that B3, what the
Ah.
area is showing, that is the area in between ingoing and outgoing rays. That is
Oh, okay.
compact region.
Yeah, that makes sense. Okay, yeah. So I was saying you need theta L, theta N less than 0. It seems as if we are at a point and locally evaluated it. Then why is it called quasi-locally? So the trick is this is not a point. This is a two sphere inside, like a cross section. So you need it all along the two sphere, theta L, theta N less than 0. Then it's a trapped surface. So local because you are defining it at a point, you don't need global infinity. Quasi because you are needing this on the entire two sphere. So that's a notion which we will proceed with. This is the fundamental, not this, but marginally outer trapped surfaces are the fundamental building blocks. Oh, I think I have a slide in the appendix, but okay. I'll define marginally outer trapped surface. So mods is the building block that we're using. In that, one of them is 0. The other one we don't have like a strict notion. So one of them is 0. Other one we don't have anything. This is actually close to apparent horizon. So numerical relativity, there's apparent horizon, but they I think have less than 0 for this too. But we won't be using that because in numerical relativity it's required for stability. Theta n less than 0 is required for stability. So what we do is we build on these mods. So I have one mod and I like build like the tubes of mods that'll become this non-expanding horizon, and that's the central notion that we want to start with. So as I mentioned, it's r cross n. So r cross n. This is like the time coordinate that goes over time, and n is the mod that we started with mods.
So that R cross n is your apparent horizon, or what is your?
So apparent horizon will be outside this technique, like it'll be the boundary of this region. This is a non-expanding horizon because
this is the definition in your.
Yeah.
Okay.
Because
So generally it says that means in general definition it is that the apparent horizon is the foliation of these nodes.
yeah, but no, there you need also this, I think. For apparent horizon, this is considered. But in ours, we are taking a general.
Okay.
So apparent horizons form the external boundary. But this is the reason why it's different is, this is a side track. Like if you have binary black hole mergers, if you do the apparent horizon, you'll have a jump when like it joins. But this is a smooth surface which goes and smoothly joins. That's just the difference. Okay. This is the definition of non-expanding horizon, but that's a very basic notion. We want a bit more than that. We want to constrain the derivative. So can I write that side a bit?
It's a bit blurry.
Oh, okay. Oh, nothing is seen. I think now it's clear. No.
Doesn't get better.
Yeah,
It's
just
because we are talking about the expansion and it's
yeah. This is actually the focusing theorem. So it's it doesn't have autofocus or what.
we have this.
If you don't appear in the frame, it will focus on the bird.
Oh, but
You
it's
cannot write.
Yeah,
Write like
because it's on you.
There is issue with camera.
you should have pointed it out, but it's okay, I think.
The camera is trying to adjust itself.
It doesn't get better. This works.
So for your case, this theta n can be means what should be the value of this positive?
It actually constrained later on. There'll be a constraint, but it's not. No, it can be positive also. Yeah. But negative case is exactly apparent horizons. But a lot of cases, mods.
It doesn't get better than this.
Oh, that's bad. Should we call them?
There is no time for.
Okay, I'll just continue. I think we can.
Maybe I.
Or should I try turning on my camera and share?
Is this one based on some paper? Or?
Yeah, I'll present. These are a series of papers which have this isolated horizon framework. So Ashtekar, Badrikrishna, and all so Badrikrishna is my supervisor for the thesis. My work is
So
into tidal
if
deformation.
you write like here, we can see.
Okay.
I mean, just
Okay, I'll erase
in
that
that
copy
area.
and write
Maybe
that.
a little zoom out. That. Okay.
Yeah, all this until now is more or less what is usually done, but this notion is slightly different. So we start with non-expanding horizons. Here it's fine, right? Yeah. So I told you about this, where these are theta n less than 0, theta n can be anything. This is like the foliation of mods.
There is a filter in the camera that causes this.
Is it fine now?
I mean, let him continue.
Go ahead.
Yeah, so the idea is we do a weakly isolated horizon. So the thing is, from non-expanding horizon, there's a notion of the intrinsic derivative. So you have the derivative of the entire spacetime, but on your hypersurface, when you constrain it, that will give me a theta. I'll probably have a hat here. This can be written locally in terms of operator. This is a bilinear form. So theta alpha of L beta can be written as L, the actual vector. So L is the normal which you are considering. And cross omega. So this omega is not the twist omega. That's 0. We just forget it for now. This is a rotation scalar which you can define. I call it rotation because in Kerr it will be very evident that this becomes it's related to the spin of the Kerr. But this is the important scalar which we'll be working with. It's basic. Whatever I say to this, it more or less implies this. So I'll be referring to this scalar. And the condition is we don't want its Lie derivative to change. So, as in, we say that it should be constant along the hypersurface. So, everything I probably put a hedge because it's all on the hypersurface. So, this notion, I think I have an expansion also. Yeah. So, more or less, this is like the zeroth law of thermodynamics. So, if you can see, I've just expanded the Lie derivative. What I have is the intrinsic derivative acting on kappa. This is both of these are equivalent statements, is 0. This is the zeroth law of thermodynamics. The surface gravity is constant on the horizon. So there's another term, but that because of hypersurface orthogonality, that becomes 0 too. But in another way, I can write this, and that gives me something like this. So the same statement, if I want to write it in terms of this, that is the commutator of the derivative, and this is 0. I think it's this. That is 0. But this, in fact, if you see, what does it say? It just says that the overall derivative restricted to the hypersurface has to follow some constraints. This is shown that this is possible for any spacetime. So that's why it's weak. We want something more restrictive. We don't want killing horizon, that is the general one. But for that, you need a global killing vector field, again, global methods. So we want something more restrictive. So this formulation, if you see, it's one component. The L, I think I'll call it time. Like later, you'll see it'll actually be the time vector. N is the radial vector. So it's like the temporal component of the intrinsic derivative is zero, some formulation. But we want more restriction. So this whole commutator is zero, the isolated horizon. And for our cases, I think we can work with non-expanding or isolated. This is a very restricted framework. Not all spacetimes have isolated horizons, but all black hole spacetimes have. So, but you can find a weakly isolated horizon easily. There's like an invertibility operator, which is always inverse. I mean, there's some details which I'm pushing under the rug. So for most of it, I'll be using this, but there are some aspects from this which is borrowed later on. This is more or less what's been used in literature also until now. But this new formalism is of isolated horizon. So basically, it's you go step by step constraining the local operators. Yeah, this is the definition. So I think this was also presented last week. So what we are assuming is equilibrium situations. But beyond equilibrium, there's dynamical horizon, which I have not explored. So that's when you have, so in our case of non-expanding isolated horizon, the area is constant. So we assume in that regime we work, but there'll be some incoming radiation, outgoing radiation,
So
etc.
that part, the parallel part is the
Yeah.
non-expanding.
Non-expanding horizon, yeah. And in this case, you can have radiation far away. Close to the black hole, there's nothing. So it's a local formalism, right? And this is null hypersurface. It becomes space like up and below. So there's a transition. So
for this dynamic horizon case, these both are expanding, L and N.
No, right? Inside it, I don't remember how this is. The dynamic one is expanding, I think.
But the picture is shown that L and N are both outward direction, so I'm asking.
Maybe. I'm not sure. I don't know what the definition is, but the way it's defined is actually different. There's one more condition you have to define quasi-local horizons, which dynamic is. So my study is just isolated, equilibrium itself. But I don't think both are expanding. Yeah, that's not the case. I didn't make the plot.
This part of thought. So I see it is not expanding this horizon.
Yeah.
So what is why it is not expanded because of radiation?
Because it's an equilibrium condition. So our study isolated horizons is more or less equilibrium black holes, but in real life it's dynamic, right?
You mean okay? We have area increase now.
Yeah. We assume that the area increase is negligible. It's very small because we are assuming theta L 0. So area comes from theta L and theta N. We are assuming that the area increase is very small, so that does not affect us.
So here, why is decreasing? What is decreasing here?
Oh, the cross-section area is like the area. This is, I think, when radiation goes out. This is quantum, so it's time-like. This is classical, so space-like. Null. Hawking, yeah. This is I think that's why it's drawn in dotted because otherwise it does not decode. Yeah. This is, I think, space-like, null, time-like. We don't study time-like in classical, right? It's just space-like or null. So this is usual expanding, non-expanding, and quantum. I think that's the case. But Ariadna, she was there last week, right? It's in her thesis. But my study is just here, so probably the equilibrium case.
Actually, it is also similar to apparent horizon behavior. Apparent horizon also, when it's expanding, it is space-like.
Yeah.
And when it is shrinking, contracting, then it is also.
Yeah, that is a general behavior, right? Expansion will make like here you'll get the null equal to 0, like L dot, the metric is degenerate on that. So that is a general concept. So yeah, our case is more or less here. Okay, so my idea was given this, so usually how it's done, we want to.
say it is, you mean near horizon, that NEH, right?
Yeah,
Why you say it is equilibrium?
because the area is not increasing, right?
Because when we say in equilibrium, that means it's same temperature as outside in thermodynamics.
Oh, this,
Thermal equilibrium.
yeah,
He's saying about thermal equilibrium.
So, but
this is not thermal equilibrium. This is more or less like there's nothing that changes the area of the horizon. Yeah, I think temperature of a black hole is a bit the thermodynamic equivalent. But we prove the zeroth law, which is like the temperature of the black hole is constant on the horizon. It just says the horizon is the equilibrium surface. We don't talk about how it radiates outside inside. Um, yeah, this is the framework.
maybe stationary.
Yeah, these are stationary. Yeah. Locally stationary, not global, because we don't know how it's global.
We say equilibrium, or we say equilibrium thermodynamics.
Yeah, can you mean dynamical, like if you only consider GR, then GR also you can define some equilibrium, dynamic equilibrium. So that is, I think, the dynamic.
Yeah, but I think local stationarity is a good, because stationary is also bad because global stationary is mentioned. Then you need a global time like killing vector field, which is not there. We don't need that. Concepts are local here. So, yeah.
One more question. So, if you define this particular horizon, and on that horizon, if you can define a induced metric,
Yes.
and from that induced metric, you can always define an extrinsic curvature on the surface.
Yeah.
That extrinsic trace of the extrinsic curvature, when it is less than 0 or greater than 0, it defines that whether it is contracting.
Yeah.
In that way, also you can actually explain all those.
Yes, that can be done. But for that, you need to know the form of the metric, right?
Yeah, that can be.
No, here we don't assume the tetrad. We find the local tetrad at the end. So this is usual approach is you define a coordinate system locally, then perturb it. Even tidal deformalities, which will come later, we are not assuming a coordinate. We are just assuming gauge choices, which is more or less the same. But these are physically motivated. Like at the end, you don't say this is because physical motivation. Like it's a ground up approach, I would say.
But
So
what else? Yeah, you need a frame. You need to define some now.
yes. You need this you find the tetrad in using some gauge choices and Einstein's equation at the end. So the idea is I use this characteristic initial value problem. I think a better picture is this. So I have the horizon. I think I probably explain it here. So I have the horizon. I take like this. This is one mod. I take the Pasch null cone. In that, I specify some data and I specify data on this. So on the cross section, I have these data. I'll come to what these are. And on the horizon and the partial outcome, there are some data. Based on that, I find out the entire spacetime inside this. So that is the idea. I give some data. Like the usual way it's done is Cauchy initial value problem, but that is 3+1, where it's space plus time. But here we are doing a null formulation. So we need two transverse null hypersurfaces. So this and this is transverse, but it looks like it's not because it's in 4-dimensional transverse. And I specify some initial data and find the whole spacetime in this region. How much time do I have? I think I can, because the other part is also GW. So I wanted to give good importance to both.
20 minutes.
Just 20 minutes over. Oh, okay. Yeah. So
we have around 20 minutes.
Oh, that's all. Okay. Then the idea is, okay, I'll just say it verbally. There are some Hamiltonian calculations done using this isolated high horizon framework. That'll give me the mass and surface gravity. So usually mass is done ADM, right? That's at infinity. But using this formalism of isolated horizon, you can calculate the mass on the horizon, which is a local concept, which I have not done. It's been done. I've just used that. And I've used some initial data gauge conditions. And there are some equations. So Newman-Penrose field equations are some complicated looking equations, but they're just Einstein's equation rewritten. And based on this, I find local tetrad and also extend it radially. So I'll just, okay, sorry. I think this is important because L and M are the independent components I told you. I define directional derivatives. And if you see this V is like a temporal coordinate and R is like the radial coordinate. So I'll I want to show this and that, so I'll probably write it here. This is the horizon. This is the mod. So L is like this, the temporal coordinate along the horizon. So it's more like moving in time. Radially extending outward is along this. And the other M and bar are on the horizon. It's the transverse surface. So giving some coordinate frame expansion like this, I find the exact U, X, etc. These are unknown. These are directional derivatives as the normal case itself. So I did this for Schwarzschild, it worked. Then the actual interesting part of the thesis was tidal deformities, it's just perturbations.
So what is that? Something is falling into the horizon.
Which one?
So this cone.
No, this is just the past null cone of this point. Like
Yeah. So if you have in that surface,
yeah,
initial surface something which is actually falling into.
yeah.
You are taking something some initial condition on that
On
surface,
that, yeah, yeah.
in that
Yes.
ground surface. Okay.
Yeah.
So then you want to see that how these particular
On the entire
effect on
space-time
the-
inside.
what should be the effect on that horizon?
Not just horizon, on the entire space-time
Yeah,
here.
the
So
entire
all that, this entire space-time is determined by this initial
So
data.
I'm asking, what does this physically mean? That means something is falling into the horizon? Or?
No, this actually kappa L is actually on the horizon also. So this data is not very important. It just defines a coordinate. So it's more or less defining the time evolution. It's not a significant thing here. The important data is on the horizon itself. So everything is determined on the horizon, which is this. But I agree, there's one thing which actually is like the temperature, extrinsic gravity that you define on the past null cone. This is basically the initial data. You provide some data and it extends the space-time. This gave me Schwarzschild, which is easy because it's spherical. It's also done for curve will be technically hard. Okay, I did it because at the end, the global picture was to study tidal love numbers, which is when there's a black hole, but there's another external. So this is a self-gravitating object. There's another external object because of which it's more or less like electrical polarizability. I had some points which I had to say. Okay, but probably it's a bit of detail, but the idea is so what happens? There's a black hole which is self-gravitating. It's more of, I'll do the electrical analogy itself. So if you have an object in the charge field, that will polarize and that will create some internal fields, right? And at the end, the potential is something that comes because of it, the original phi naught, plus because of the external field, plus because of what it has done internally. So we've studied the response of black holes, and that gives an external potential like this. So L by R is the normal potential. There's one part which is the response, one part which is the actual tidal field. And there's this ratio which is called love numbers. It was studied by Love, who studied the moon and earth system. So we want to see if we can determine this by using this formalism. So the idea it's usually done is like black hole perturbation theory itself is done by defining a local tetrad and perturbing it. But here we want to give some gauge choices and see what comes out of it. It's more or less a more informative approach. This is how we extend because there's the side too, which is the wild scalar which we use, which is basically the curvature. So we related to that. I'll skip details here. Yeah, the important part is it's a perturbation. So I assume there's this cross section I was telling, right? That has a metric, but I perturb it. So there's a 1 plus p hat. So about the background, I perturb it, and it's usual black hole perturbation theory, which actually gives us the same equation which Weil had done. So, Tukhonski's equation, which is basically this is for vacuum, otherwise there's a source. Something acting on psi4 is 0. So now I'll shift to gravitational waves because psi4 is the important point. It's okay, right? I have skipped a lot of details, I think, but in the interest of time. So we know gravitational wave observations, they have been, it's like the golden era of gravitational wave astronomy. I think this is the GWTC4, where around 200 signals have been discovered, etc. This is a YouTube video, I'll probably skip that. It's just how the waveform is. And why gravitational waves? Because there's a lot of things, but some of the interesting things I'm studying is nonlinear strong field regime. And I'll say how it connects to what I did in the first. So we have this binary black hole. This is probably one case where the other mass is very big, but I think this is the effective one body how they use. But basically, we use perturbations about a background metric. So we have a flat metric and perturbations about it. And in some, like either we can do EOB or TT gauge, that'll give us gravitational H, the strain. And that, in fact, is related to psi4. So something that you define along the horizon is actually which radiates out. So psi4 is, in fact, if you draw it like this, psi4 is something that is radiated to infinity. I mean, there are other things too, but the interesting one is psi4, which at infinity gives the strain. So strain as in the second derivative of the strain. So in numerical simulation, it's just double integrated over. So this brings the bridge. And some of the interesting outlooks in LIGO, at least, is one of them is testing whether it's Kerr, that's the black hole spectroscopy, nonlinearity, eccentricity, and further detectors. So these are some projects I've done. I'll probably skim through the details, overlapping, and these two, I'll skim through some of the details. So overlapping gravitational waves, it's a problem when you have one gravitational wave and a counterpart that is there that are similar in time and frequency. So if you do time frequency spectrograms, they actually look, the chirps overlap. This is a problem because we usually, like LIGO first does single signal tests, right? Searches are done for single signals. We don't want this to bias results for like when they are not separated enough. So if you see here, the separation is below 0.1 seconds. That's the pi-CBC trigger window. So things which are close enough, they'll actually cause beating patterns. I agree these for the current detectors, they are not, the rates of these mergers are low, but advanced detectors will cause a problem. So our study was to study this degeneracy with lensing. I've plotted this overlapping signal here, and if you see there's some, okay, I think the previous plot itself had a better, there's some beating patterns that you see, the dotted lines. That is similar to what lensing is, or even eccentricity precision. So this study was done in that sense. This is more or less a data analysis study where we use Bayesian inference, calculate the Bayes factors between a lensing model and a single signal model. There's also other methods which we use to extend it to a population because Bayesian parameter estimation is expensive. And we have a lot of we have different signals that we use: unlensed, type 2 lens, micro lensing, eccentricity, spin precision. So the idea is all these are single signal effects. So this affects a single signal. These are astrophysically motivated. But what if it is mimicked with a overlapping signal? So we have some evidence. We have put a paper out for this. I'll just skip over the details. I think it's 10 minutes.
We have 10 minutes.
Okay. Just the idea is we have some overlapping, I'll just summarize the idea. There are overlapping signals with similar mass, similar SNRs, as in the two separate signals, and that mimics lensing. So that have degenesis with lensing. We have obtained high Bayes factors for that. There's a region of the lensing parameter space which actually has high Bayes factors. So all the circles that you see here have higher Bayes factors, and that is in overlap with lensing. We have considered the range of chirp mass ratios, SNR ratios, and delta TCs. Basically, these are the relative parameters of the two signals. So one signal, MB, SNR B, TB, and MA, SNR A, TA. The MB by MA, SNR B by SNR A, TB minus TA. These are the relative interesting quantities. Summary is the results show promising sign of overlap with the overlapping signals have an overlap with lensing. And we also have new results for spin precision and eccentricity, which will come as a follow-up. So there are some promising signs of precision. So the overall idea is an overlapping signal, which is two signals, is biasing something of a single signal. So with further detectors, this is a problem. Now I'll again completely switch track to ring down physics, which is another interesting project. Um, we all know the ringdown is described by quasi-normal modes. These are the fundamental it's more or less like spectroscopy. You have some signature of the signal which actually tells about the horizon or even about the black hole. So there are fundamental omega LMN, which are these quasi-normal modes. And that is a very important study because it tests GR, and at least with the recent signal, the 250114, is actually we are also working on I and Jayed. We have like some notion of even a quadratic mode that we have observed here. So this plot might change with that, but the idea is these quasi-normal modes actually have so much information about the signal. So our one other study that I'm doing is incorporating eccentricity. So B merger is basically an impact parameter. So when eccentricity is the definition in GR is not gauge invariant. So there are some other parameters. This has the Newtonian notion of how close the signal is at one of the. So that more or less is eccentricity. So against eccentricity, you see that the waveforms of the ring down are varying. So in EOB, it's the in spiral that is done. So a lot of waveforms just focus on in spiral, but now we have high SNR ring down observations also, and we want to effectively map numerical relativity simulations into phenomenological models. So this study was that. And there's some detail. So we use some functions like this to fit the amplitude and phase of the post merger.
These functions,
It's actually, so first of all, there were EOB studies which told that in spiral to merger to ring down is very smooth. That's a smooth transition. And based off that, there were some estimate. It's by seeing the numerical data, there were some older functions that were used. But we wanted eccentricity, so we had to modify those functions also. But
what is C1,
yeah, these some of them are free constants which we are fitting based on numerical data.
Is this similar way that we are doing the, I mean, I think connect.
Yeah, it is more or less,
Phase
yeah.
and amplitude, right?
Yeah, those continuity conditions actually fix a lot of coefficients, but there are also free parameters that we have. And those free parameters we use numerical relativity to infer.
How about, what do you think if we use this ways of connecting? But this is for
But this does not tell about quasi-normal mode. It absorbs every information of the. It's just a good waveform. But if you want to extract separate quasi-normal, this is per mode. You have this waveform. You have to sum over all quasi-normal modes. You'll have that. But this is just like quasi-normal mode is a damped sinusoid at the end, right? This is one of the form. It's a there's a tan.
And these are that exponentials.
Tan hyperbolics. Yeah.
But then
yes.
we worry about that.
Yeah, this can actually, this, if you see it, more or less looks like a quasi-normal mode spectrum itself. This is how the ring down would look with these functions. So these have, yeah?
You said that you compare this to numerical
Yes.
relativity waveforms, but there are not many numerical relativity waveforms with
We-
eccentricity.
The SXS has a new catalog with eccentricity. RIT has a good eccentricity catalog too. But RIT, Rochester Institute, their catalog has some numerical issues at late times. We just use till 80 M after merger. But also now there's some more, I think last week too it was mentioned. There are some new eccentric catalogs.
For this type of functions,
Yeah.
ring down type, what you have written that may not be unique. So because there can be other function which can be.
Yeah. This is just a like at the end it's a phenomenological model that you're using, right? You don't need like from this we are not extracting physics out of it. We are just
You are not extracting from that function.
no, in some sense we are extracting from the overall function. It's not from the individual coefficient. So the individual like it's more or less like the individual coefficients can be different and form can be different, but at the end what you see is the same thing, right? Like from NR you know the for non-eccentric if it looks like this, for eccentricity it may look like this. This physics you can extract, but what function you fit does not matter.
So what I am saying is this constant what you consider there,
Yeah.
that function, those constant, if it is if you can write down the ultimate function
Yeah.
of that particular ring down thing, that means this constant can have the information of mass, spin of
Yes.
a charge maybe. So
Yeah.
all those things of the
Yes.
black hole inside it.
Yeah. These internally have dependencies, and that's what we're fitting actually. So The
But
numeric,
you don't know how, because this function may not be this function.
yeah,
may be
yeah,
other
like they could be a true function with true coefficients. This is one function with its coefficients, and we are actually fitting those free parameters.
So
So
you're
yeah.
basically just using this for detection, but you don't want to do any parameter extraction with that.
You
So
can do
basically what-
parameter extraction, right? Because it's motivated by the inspiral into this.
Yeah, but I mean, like you don't use the ring down because you said this functions that is a phenomenological waveform without
Yes.
physics inside. So this means you cannot extract any physics.
No, without physics is actually bad way to phrase it, I think. Like IMR phenom is still a phenomenological model and it has physics inside it, right? So the coefficient, I'm just saying the form of the function may not have important meanings, but like each of the coefficient will have internal dependencies. It's
Yeah, but you said those are basically random.
No, that's with respect to this function. Like if I say C3A, it means that with this function, it's C3A, right? It's not a general, there's no unique notion of C3A per se.
Yeah, but basically, I mean, let's say you have two modes
Yes.
that differ by a factor of 2 in their frequency.
Okay.
So this could fit any of the two modes perfectly well,
Yeah.
or it's a mixture of the two modes.
Yeah.
But the two, like having one mode or the other, may correspond to different black holes.
Yeah.
So in what sense can you extract the physics?
No, the physics I meant to say, like there's okay. What it's basically this. So you can't do NR simulation for every GW observation that's there, right? Or every parameter estimation you do. But you know some NR simulation exists for E1 and E2, different eccentricities, and they look very different.
Okay.
Our idea is to model that. Now, say we have a gravitational wave detection with this new template. That'll give us some sign of whether it's close to E1 or close to E2. Like it's more or less a mapping of the new, it's like a surrogate thing that we do, but not exactly.
Okay, so when you say you can extract physics, you mean that you can see, like uniquely recognize that there is eccentricity.
Eccentricity, yeah. The study is made.
Other physics might say
Yeah,
okay.
there's still in this case also this is for one mode, so there'll be mode summations too in this, but we have just done it for the 2 to 0 now. But the mode summit, like this is all done for just 2 to 0. So as you say, like you can do it for 2 to 0 plus another one which has half the frequency, etc. This is basically like one quasi-normal mode type thing, but modeled into something we can study.
So how many constant these constants
Three.
are there? 9? Or
No, like in the quasi-circular case 3, but here it's 5 that we are wearing.
okay.
These are fixed
Okay.
because you did like the amplitude at merger, phase at merger, etc. should be the same. Yeah. And even derivatives. Yeah. And we have, I don't know if I didn't put the plot, but we have like these vary across the eccentricity space. So at the end, the waveforms vary across the
So is
eccentricity.
there any other model where greater than these 5 or less than these 5 constants are also?
Yeah, quasi-circular case is just 3.
Oh.
But it's quasi-circular. You can't do the. Also, I think in quasi-circular, one more issue is this amplitude at merger is just constant. So it's a wrong model. But with the eccentricity, the amplitude at merger changes. So there are things like this which we have to do. This will also come out soon in probably the next one.
Okay, so you're saying for a quasi-circular case, it's unique because you have less functions, right?
I mean, unique as in this is just one model that is proposed, which has already been used. So all the tube-Birisamas, etc. waveforms have this model. But now our with eccentricity, this is an extending model.
But can you also read out what eccentricity you exactly
Yeah. So it's more or less like that. So I have a function now. The procedure is there's a numerical relativity catalog. I have all these coefficients. I make them functions of eccentricity. So I recur with each case and plot what C2A is, what C3A is. All that is done. And based on that, I have this global fit of the coefficient. So that gives me like this as a function of eccentricity, this as a function of eccentricity. So at the end, this as a function of eccentricity. So you do the reverse thing, right? I'll probably explain it in detail later.
Yeah. I mean, I get the idea.
Yeah.
Just in
So when
I'm not
you're
sure.
only calculating or trying to see whether what is the eccentricity, then this function may be helpful. But if you want to extract other physics, it is not helpful.
I mean, it's one model which is like more complete than what is used before. So what is used before was the quasi-circular case, which is in these T of isomers, etc. This is incorporating eccentricity. So slowly you do all like it's that's how we grow, right, in this waveform modeling. So
We should then move on.
sorry.
Maybe you can move on.
Yeah,
Yes.
just
I had also discussed this in one meeting. So this modeling with the function.
Yeah.
So
But look at eccentricity, right?
not
I wanted to do it with machine learning.
Oh.
There is a software
For the
machine learning
ringdown.
that suggests the function. You give the data and give
That's
the
impressive.
uh,
I mean, now it's there for the full waveform too, things like that.
That's chosen by human.
Yeah,
It can have bias, but
that is true.
machine learning can give you the function.
Correct. Yeah, the last thing is this is all again still linear, but there are problems because GR is not linear. And with Jayed, we are actually working on nonlinear like quasi-normal modes that is seen. So I had shown you the Tikonsky equation, but now this is at first order. So the metric is expanded into second order. And the second order contribution is sourced by the first order terms in a quadratic way. So I didn't put a lot of details, but basically the thing is, if you have two linear modes that combine to give a quadratic mode whose frequency damping times and amplitudes are related like this. So that's probably, yeah, this is the way forward, I think.
For these quadratic modes, do you know that they are, let's say, dominant compared to other? Because like this is basically the second order.
Dominant one supposed to be the one that comes. It comes from the linear dominant one, which is 2 to 0. So it should be 2 to 0.
No, also,
No, I
yeah.
like this is a specific set of second order modes, right? Like you could have other second order modes not induced by the first order mode.
Yeah.
Is it known that these are dominant compared to those other modes, or is it just that you solve for this because they are easier?
No, I think only this type of second order contributions are solved, which is basically sourced from the first order modes.
You know, I mean, like, do you also happen to know that they are dominant compared to the other second order?
No, that type of, we don't even know a way to solve those type of
Okay, so
second order modes. Yeah.
Just because you can get them and the others you
No,
can't.
but also the fact is some of these are more dominant than the linear mode also because there's a proportionality constant and that actually depends on how the spin etc. is. And in some cases, the quadratic mode is more dominant than the linear mode. So, and that's probably what we are seeing with 250114. In some cases, it's dominant than the other linear mode that's there. So there are people who worked on these proportionality constants and that type of studies done.
Because we don't see all the linear modes, we just see a few of those, and we will obviously find quadratic modes from that a few linear modes.
Also, like you can go earlier to the merger time. If you do linear regime, you have to start a bit later. You don't have the notion of a start time, right? This helps us go closer and closer to merger. I mean, there's cubic, there's
But always including that you are missing actually other quadratic.
yeah.
So there is still something.
Yeah, residue time. Yeah. That's pretty much, I think, what I had to say. Yeah, there's also some other study I'm doing on quantum stuff in Horizons, which is even cool, but I think it's too much for just this talk. Already, I think I went on different topics here. Yeah, thank you for this opportunity and thank you for listening.
I have a very nice question. Like usually people say black holes have no love numbers.
Yes.
But it also makes sense that maybe I didn't get you. Like you said, like if there is a potential, then the black hole gets deformed, and then it's not a sphere, so it would have love numbers, right? So in what sense do the people say it has no love numbers?
It's actually the asymptotic love numbers. So there are two kinds of love numbers. This is the superficial love numbers, which are not zero. So we have got that the local, like it actually has some non-rigidity. But asymptotic love numbers are zero, which is the usual notion.
It only means that asymptotically.
Yeah.
But it will decay and again.
Yes, yeah, there's like physical notion of that too. And also it's just for this 4 dimension. It's a very
We also discussed in her talk that when it oscillates and then after some time it will decay again.
yeah.
Okay.
And only in 4 dimensions, and it's also noted to some symmetries that even that is a like neutron stars don't have that love number 0 thing asymptotically also. They are not Newtonian, right? Black holes. So there's some notion of ladder symmetries, etc., which people associate to. And also love numbers are some effective field theory coefficients. So they have some theory regarding that, but it's still a very surprising, even though the tidal ones are 0, superficial are not 0.
So you are working on this quantum field theory in Kaspersky for this particular quantum effect, what you are saying at the horizon.
No, not that type. It's more or less like how there are some physical experiments you can do outside the horizon, which will inevitably decoy. I can probably explain it after the talk in detail.
Yeah, I'm
Maybe,
interested.
maybe we can ask people online if they have questions, because we can still stay around and talk.
Are there people online to have questions? Apparently not.
Okay, if not, then
I'll stop sharing.
Okay, I stopped the record.
So when you ask this,